All right, welcome back everyone. This is the second tutorial for Korali for the computational science Zurich UQ and data analysis in applied science course. Let's do a recap from yesterday to remember what we saw. And yesterday we had an overview of software for UQ and optimization, and saw a list of features, what's been offered by the one we are presenting in this course, which is Korali. We created an optimization example using Korali's interface, and we ran the example. Hopefully all of you could do it yourselves at home, but you have enough time to do it later if you want. We sampled the probability of a normalized function, the probability distribution, using Korali. We could see it, the two variables that made the distribution, and we can see their covariance and all the information using the plotter that comes with Korali. And finally, we did some Bayesian inference, and we used TMCMC to infer the best fitting parameters of a model given the some reference data, which are observations from physical reality. So now, if you will, you can do it now or later. I would ask you to update Korali, and rebuild it, and also update the tutorials, because I've been updating them, fixing things that I realized yesterday were wrong, and also I added more tutorials for today. And we will hopefully finish them all, but if not, I encourage you to try them anyway, because the instructions are there and the code is there and the solution too. But if you have any questions about what's going on, you can always send me an email, and we'll see it. Okay. So I received a question yesterday regarding nothing in particular, but about what we do when we do inference. So we're trying to infer the best parameters of a model. So the question says, given a data set X and Y, with X in a given neighborhood, and a model M that produces Y equals M of X, is there a way to quantify the uncertainty of some new target variables Y star produced from the new input variables in its respective neighborhood? So what's being asked here, if I understood correctly, is that we have, let's say, time, and this is some value of time. We have observed at certain points with our microscope or with any measuring tool certain V's. So this is X, this is X0, X1, X2, you can call it T as well, doesn't really matter. And this is Y0, Y1. So we have observed from reality a set of X and Y's, and we have used Korali to calibrate a model which takes an X, but also is configured by certain parameters. And we have found the value of these parameters that best fit the data. And the model could be your good old polynomial regression or linear regression, and it will look something like this, right? If it's linear, we will have found the slope, right? And also the height. I don't remember what's the name for this in English. And so we will have found the two parameters that describe the linear regression that best fit the parameters. And there's some error here, the error with respect to what we observed, that is reflected on the plus epsilon factor we have seen before. So now the question asks, given a new set of x's, so x4, x5, x6, using our model, which may not reflect reality, we found these points And suppose that reality, in reality, for these x's, the points were here, here, and here. So is there a way to quantify or at least estimate based on what we have observed in the neighborhood of these values, what will happen in these regions? And if we only use these two parameters, the answer is no. The most we can have as information is the epsilon that tells us that at least in this region, we have somewhat of a bar of error, but we have no way to correctly project this error towards the future, whereas the error in reality in this case would be like more something like this. So I'm not an expert, so that's a disclaimer, statistical expert, but from the experience I've seen working with George, which you already know well, is that in these cases probably, oops, okay, in this case probably what we can do is to include certain other parameters, which is the error boundary or bounds. So we can say if we can give a band of error, which will be the best values that reflect our observations, and then this new parameter can be projected, but you realize that this new parameter should be plugged in the model in some way. So the model should contemplate, besides estimating the possible value of the function at those new points, also should be a model that contemplates uncertainty. And this is the point where I don't really know how to do it. You should ask George how to change your model such that besides the points this, and this that you want to estimate, it would also give you a bundle of uncertainty that better reflects reality. So you still don't know exactly the values, and you don't get closer to the actual values, but you get an idea of the uncertainty associated to your estimations. Okay, I hope that answers that question. And there was another question that said, how can one evaluate the model M if it contains fitted empirical parameters such that the parameters and the model, of course, are dependent on some data themselves? And that's what we did. So the parameters of M, these parameters are fitted by the initial data we have observed. So x1, x2, x3. And when we want to estimate, say like this, and our model was a linear regression again, just to make it simple. So we have fitted our model with these values. The question is, you would expect the model to work well on the data in the neighborhood. Of course, if you estimate values around here, you would tend, I mean, there's no guarantees, but you will kind of get estimated values within the neighborhood of the x's you have already analyzed. But then when you go outside that, for x4, x5, x6, the question is there a way to know how far from the truth we would be the further away we go from the neighborhood we were in? And the answer is the same as in the last question. You should create a new model M prime where you contemplate x and parameters prime, and parameters prime include the original parameters plus some kind of error estimation parameters. I don't know what symbol should I use here. S. Right? So you change your model to have some uncertainty contemplated into it that you can then estimate, and you can have these kind of bars that grow with time, or with growing with the distance from the original neighborhood of values you have from reality. A good example of this kind of a disparity from the reality and what the model gives you is, for example, the SIR model for pandemics estimation, epidemics, I think it's called, where the SIR model is a simple model of susceptible, infected, and recover, and kind of goes like a bell curve, but then as people get better, but also as there's the number of people that is capable of being infected reaches 0, or everyone got infected, that's the reason also, then it would look like this. But in reality, this model tends to differ from reality. So in reality, we have observed this because it doesn't take into account new, say, social distancing or something like this. So this factor ameliorates the rate of contagion, so that your model is not guaranteed. No model is basically guaranteed to reflect reality 100%. There's simplifications, and therefore you would like to add to your original model ways to estimate the uncertainty associated to it. So George would be better off letting you know what things you can do to your model to adapt it for the uncertainties. Okay. Let's review what we saw yesterday. We wanted to do Bayesian inference, and as you saw, we defined a problem in korali, and with the assumptions we know already, and we have some reference data that to fit korali and to compare what we observe on the model, a likelihood function or model, and a computational model, which is what we run, and we're trying to see how good it is, or calibrate its parameters to better fit the observations. And then the model, of course, received the parameters and the points in which to evaluate the function and return its estimated values. And that's what it does. It returns the value of the function for those points. And then a parameter space within which we do the exploration, and some kind of prior information about these variables. We may have no information, so we say, okay, uniform. Okay, so we know something. It goes from -1 to 1, but other than that, we have no information. But we can have a normal distribution where someone told us it's around this area of possibility. It's very unlikely that it goes further away from this. So the normal distribution gives us some information already. And the sigma, this was a mistake because sigma, of course, cannot be negative. So I don't know. It could be some kind of exponential or uniform, but always positive, because it makes no sense otherwise. And then we use TMCMC and run an example.
Can I ask a question here, please?
Yeah, of course.
Regarding the model.
Yes.
In some cases, it's very expensive to simulate the model in Bayesian calibration. We have a model, for example, needs for one run like in 10 minutes. Mm-hmm. So most of the time they fit the most famous thing that they fit, it's a Gaussian process. Mm-hmm. So in order to do this, they fit it, they run the simulation, for example, outside, like for example, they use a Latin hypercube to sample these parameters, which we want to calibrate. They run the simulation, for example, 5,000 times, and then they put these data to the inference calibration method. They just import the data.
Yes.
Fit in this Gaussian process in a way. So they don't, for each simulation, for example, they go call the model as a function, and the model runs.
Correct. Okay, yes. But in this case, I would argue that whatever your model here is your model with respect to this experiment, but your model may be calling even another korali within. So you may do an optimization to find out these values inside. So you can do many things if you encapsulate the problems one within the other, or do other stuff. In any case, George has very good examples. I don't know if you saw it already for Gaussian processes and how to solve that problem in Korali. The main thing is that with Korali, we don't want people having to collect data and feed it manually to either Korali or MATLAB or whatever other library you may use. We want to automatize the whole thing. Even if it entails having Korali within Korali or weird stuff to get the data, we want everything to be automatic. But it's not a matter of just convenience. It's a matter that since we want to run this on supercomputers, supercomputers have its availability, and sometimes you have to wait for days to have an allocation or hours. And it's not just run it, get the results, run it, get the results. Sometimes you have to wait for a long time. So we would like to automatize all this complex process you described such that it can run in one go automatically and make your life easier.
Okay, so in the model, we directly, in this framework, I mean, we should directly call our model directly. It's not that we couldn't, in this framework, I mean, we couldn't import an already simulated data to the inference method. We should directly call.
You could do both. You could do either. If you have already simulated data, good for you. You have it already at hand. What you do in this model is just gather the data from the file or whatever, and then push it to the results. So you don't have to compute anything. Unless, so my question would be then, in this data, do you have the results for these parameters? That would be a question.
Yes, yes, it should be, normally it is calculated based on different samples for these parameters. So we generate a prior for all of these parameters, and we simulate the model based on samples from these priors. So we would have a table containing the simulation for all the x's, the variable inputs, taking into consideration all the different possible values for these textures.
Correct. So if, for example, if you have a table, imagine you have a continuous space, which you have discretized somehow, and could be, and then when korali proposes a set of parameters, you can just interpolate. So if korali proposes this value, you can say, okay, the closest neighbor is this, and take the result for this one. I don't know. I'm speculating, but as far as I'm concerned, all of these cases have been contemplated. And the specific case, there's, instead of using the reference type of problem, there's should be one that allows for you to just get the information that you already computed. But ask George, he would be better capable of knowing that. Okay?
Okay, thank you.
Sure. And then, okay, we use TMCMC to sample this. So yesterday, we did execute this. We went to the practice file folder and we ran TMCMC, and we have seen the posterior distribution of the variables. But what we missed is that using TMA on the same problem, exact same problem, to just for simplicity or for a necessity to get the best from our sampling, to get the best sample that best fit the observations, because we want to do inference and then gather just the best so we can use it for another thing. And we didn't get enough time to do this, so let's do it now. And I will just show you the solution such that we don't lose too much time on this. So how do I do this? You share? Okay, good. Screen. So you should be able to see my screen now. And let's open our computer again and go to tutorials. Let's go to practice 5. And we have seen, let's go to solution directly. We have seen the practice 5. Once you completed all the description of the problem, you can just launch Korali and get the results and then print them. So it asks you to do the plotter tool and see what how it looks like. This may take a few seconds to open. And this is the distribution we got from the parameters and sigma. We can see that the most likely value is around this area, and we can use this inference, all this sampling information to do other uncertainty quantification operations, or we would just like to just find the best one. We have enough certainty, and we want to use this data for doing other stuff. So in practice 5 underscore CMA, I already have a solution, and I would have liked to compare, but just believe me, nothing changed, except that I changed the solver type and the population size and determination criteria. The rest of the model, problem definition, distributions, and variables are all the same, except that the CMA solver needs in its algorithm to have a strongly defined lower and upper bound of exploration for the variables you are you want to use. Either a strongly defined lower and upper bound or an initial mean and standard deviation. But one of those should be defined, because otherwise from -infinity to +infinity it wouldn't know what to sample. So this needs to be defined. And another thing is that the prior distribution has nothing to do with CMA. It has to do with the Bayesian problem. It affects not the selection of the samples, but the calculation of the posterior. But the selection of the samples is just CMA doing its stuff within this region. So what I want to illustrate with this is that you can change the way you solve it, you can change the algorithm you use, everything, without having to change the definition of the problem. I personally believe that that's very useful, because the problem still remains the same. You wouldn't want to alter the way you have described it just because you're using another way to solve it. And then you can gather all the results you want, different types of results, just by changing the solver. And then if you run this CMA, you don't get the distribution, but you get the best values, right? And these are within the region we have seen of most likelihood values. These are the peaks. There are funny times where the optimal sample doesn't coincide with the region of most probability density. And these are functions just like Rosenbrock function, which is a funny one. I think it's this one, but I may be wrong. And the Rosenbrock function here, I had it, but it's gone here. I believe that what happens with this is that, come on. Okay. The point of higher density is on the crosshairs, on the white, on the yellow. I think something like that. Or no, it's on the right. That's the peak. That's the optimal. But the higher density of probability, if you take a bigger area, is within the lower range. So in that case, CMA will give you a different result as what you would see with TMCMC. But these are very strange cases. Okay, moving on. Let's go back to the iPad. Since we did this pretty quickly. And then let's take a look at a study case. I think most of you or all of you have already understood what this is about, but there's no replacement for a good example. And let's see what did we come with to show what you can do in reality with these tools. So imagine this case. You have a two-dimensional plate of metal or whatever material you want, and underneath the metal, and you cannot see them, exist 3 or more or less sources of heat, imagine like a candle or a torch, that start heating the metal plate from below. And the metal plate dissipates the heat from the sides, and let's forget about the top, just the sides, in a way that, given a certain time, it reaches steady state, in which the amount of heat that is dissipating from the sides and the one coming from below, quote unquote, is the same. Thus, the temperature map doesn't change. And we happen to have 10 measurements via laser, or we have a thermometer on the surface, 10 measurements of temperature at random locations, say. This is what happens when you start heating the plate and it dissipates from the sides. At some point, given infinite time, it will reach steady state in which the heat map will look like this, with hotter regions where the candles are or the torches are, and colder places where mostly closer to the boundaries and also far from the candles. So at some point, it doesn't change anymore that we can perceive, and that's the steady state. And that's where we make the measurements. So can we infer the location of the 3 heat sources beneath only using the measurements of the temperature above? And this is it may be simplistic, but it's a perfect example of Bayesian inference. We have measurements that don't correlate with the parameters, and we want to infer the parameters based on those observations. Well, when I say don't correlate, they do correlate, of course, but they are not directly measurements of the parameters. So it's a way of indirectly gain information about reality. Okay? So again, the experiments of Bayesian inference, we use the likelihood by reference data as before. The model will be a C++ 2D heat equation, and this exists, and we will see it working. And the parameter space will be 7 variables. They are the x and y of heat source 1, the x and y of heat source 2, and the x and y of heat source 3 plus sigma, which is the error that our model gives. And then we use TMCMC to sample their distribution of all of them, all 7 variables. We expect to run this and get an impression of what's the most probable distribution for all of these sources or all of these coordinates plus sigma, right? So let's do this practically. Let's go back to my computer, and then let's head to, first, let me show you the steps. Go to practice 6 folder. And step 2 is, well, let me clean. Step 2 says compile and run. You only need to do make clean. I don't know if the curriculum of this course asks you to have knowledge of C++ beforehand, but this is already, everything's done for you. And the things you need to change are only korali configurations that are extremely similar to those that you have seen in Python. So at this point, from practice 6 on, you don't need to program anything, just change parameters. So to compile, just do make clean and make. And given that you have the compiler in your system and everything already installed, it will work right away. So step 3 says, gather information about the possible heat source location. So in this first experiment we will run, we have a single source, meaning if you go to single source.cpp, in this first simple example, we have only one torch underneath. There's only one source of heat that can go, and the coordinates of the metal plate goes from 0 to 1. We agree on this, right? From 0 to 1 meter or whatever, but this is the 2D dimension, 0 to 1 and 0 to 1. So you can see here that we will use TMCMC. The problem is of type Bayesian reference, and we will use this computational model that we compiled against, and this is a header file that contains it. We don't really care, so feel free not to even take a look at the model because it's already given to us. And then the model itself also gives us the reference data. So if we call this this vector that already has been defined, we get the reference data, which is the 10 positions of the thermometers and also the value for them. So we have everything we need to run this. And what I will do here, instead of having Korali print the results on screen, well, let's just run it first and then see what happens. This is no longer a very fast operation. We are running 500 full simulations every time we run a generation. And we can see first, let's take a look at the distributions, how they look. In the meantime, I'm accessing the results in the application itself to print the best one that we found. So I looked among all the samples, the one with the best posterior distribution, and print that on screen manually. I showed you that later. So you can see here that for position X, the most likely value is within 0.3 and 0.4, I guess. And for position Y, of the only heat source is around this area, 0.8. And sigma has this value that we may deem too much or too little, depending on what the precision we want to find. One thing, though, I want you to take a look at. These cases have data input, and this data input for the single heat source problem has the positions in which the thermometers are. These are 10 measurements, and the exact, quote unquote, exact value that have been detected by the thermometers, but we have added on purpose. So these numbers came from the actual simulation. So technically, if we use these numbers as reference data, we will have sigma 0 because the model is representing the model itself, and there will be no error. So what we did is take those numbers and added an artificial noise randomly generated by a Gaussian distribution, such that we simulate that we are gathering our data from actual faulty instruments with their own uncertainties. It's a little bit a tricky thing we did to simulate reality, and you don't actually need to know this, but such that you know where these numbers come from. Okay, so sigma reflects the noise we added, and more or less we got a very precise or somewhat precise description of where this heat source may be. And in fact, if you look at the exact results, 0.3 and 0.8, we're pretty close, right? Would you agree? I would say so. We're pretty close, depending on your necessities. Okay. Now, let's take a look at the multi-source experiment. And if you go to multi-source, the difference with the first one is that we're using a larger population size, and you will see why. Well, I can tell you exactly why. We are using here 7 variables, and the more variables you define, and this is a heuristic, of course, I don't know if there's a proof for this, the more samples you should use per generation to get a better result. Otherwise, there's not enough. Suppose you have 2,000 variables. If you just use 1 sample per dimension, that wouldn't be enough to get a good idea of the distribution of that dimension, I don't think. Okay, so we have, in fact, position x0, position y0, that's the x and y of the first heat source, that's the x and y of the second, and then the third one, and then sigma is here, right? So 7 in total because we have distributions, variable 0 here. And if we take a look at the input file, you will see, in this case, we have 20 measurements. And we did this by experience, how do you say, empirically. With less measurements, you don't have enough information or measurement data to have a certain a precise approximate inference of the variables. So you need more measurements. Only 1 or 2 or 10 wouldn't suffice in this case. And these are the exact solutions, right? So let me copy this and have them visible at all times, because we want to see what happens here if we run our experiment, and see that the variables have all been defined with priors from 0 to 1. So the 3 candles can be anywhere in the underneath the metal sheet. So let's run this multi-source. It may take 4 times longer because we are using 4 times more samples, I think. More or less to take around 30-40 seconds to run this completely. So in the meantime, if you have any questions, this is your time. All right, it finished. And let's take a look at the distribution we have obtained from there. So to begin with, it is kind of evident that the results are not even close to what we expected from the exact solution. Not even close, right? There's no correlation with the exact solution we would have wanted to see. And take a look also at the distributions. It is pretty evident that there's something going wrong because there's no peaks almost. There's somewhat hills, but the distributions are all over the place, right? There's a huge variances, and there's this kind of a spots you see here are indications that there's some kind of confusion on the part of the sampler as to what could be the best parameters for this problem. And also sigma seems to be much higher than before. So it's telling us that this model we are using is not quite reflecting, or there's something wrong in using this model that is not quite reflecting reality. Does anyone have a clue of what happens? Why was it so good at describing the position of 1 candle, but then when we use 3 candles, it went crazy? Even though I can tell you I can guarantee that the number of samples per generation is enough, and also that the measurements, the reference data is also enough. What can be going wrong? Does anyone have any idea? Let me add the file again. You can either use the chat or just unmute yourself and suggest a possibility.
Maybe it's the number of parameters that you've calibrated.
No, good one. But as I said, the reference data and the samples per generation should be enough to very well represent these 7 variables, parameters. So let me, if no one else wants to suggest anything, let me spoil the solution and tell you that what's failing here is not the model, it's not the number of the reference data we have, it's not the number of samples per generation we are using. It's that the problem is ill-defined. And if I could illustrate that with paint, let's use paint for this. It's never too late to use paint. This is the metal plate 1 by 1, and we say that the heat source 1 can be anywhere around the whole plate. What can we use? Let's use this. So heat source 1 can be everywhere. Heat source 2 can also be everywhere. There's another one. And heat source 3 can also be everywhere. And the problem with this is that this result of heat source 1 being here and heat source, let's say another color, and heat source 2 being here would represent the same solution as if heat source 2 was here. I didn't mean to do that. And heat source 1 was here, right? So there's ambivalence. There's too many solutions. There's infinite solutions, give or take, for the problem we are putting here. So how do we solve for this ambivalence and force TMCMC to find a single solution? Well, in this case, we need some kind of prior information. There's no other way. Basically, either you change the model to not accept solutions that can be symmetric, or you gather some information. In this case, I'm giving it to you in the slide, and say, someone came to us as a worker in the factory, for example, and told us that the machine that they're using to heat the metal plate cannot place 2 heat sources in the same quarter of the plate. So there's 4 quarters, 2 of them cannot be placed in the same position. And furthermore, they're using 3 heat sources, and only and the lower left corner is not being heated directly. So now you have enough information to change the problem into being ambivalent to being precise. And with this prior information, we can change our problem definition to stop confusing TMCMC. So see there in the diagram, source 1 belongs to the upper left quarter. So it means that its x-axis goes from 0 to 0.5, and its y-axis goes from 0.5 to 1. Everyone follows? There's no questions about this? The other piece of information we have is that the x-axis, the x position of source 2 goes from 0.5 to 1, And again, it's on the upper quarter, so it goes from 0.5 to 1, also in the y-axis. And heat source 3 is the only one that's below, so it goes from 0 to 0.5 in the y-axis and from 0.5 to 1 in the x-axis. And now we have a better defined problem with this prior information we gathered from asking questions, basically. Now let's run it again. But first, recompile, because C++ needs to recompile Windows changes, and observe what happens. Let me cheat first, and such it doesn't take so long. I will explain what I will do now, but just bear with me. I will explain it actually in 5 minutes, but just without such that we don't take so much time waiting. And rerun our problem. And print the results. Check the exact solution, and you can see that they are pretty close to what we inferred. Now that we know this prior information, TMCMC doesn't get confused anymore, and it's well defined, well constrained, and the results are very similar, barring some artificial sigma we introduced using a Gaussian distribution. And here, these plots are very adaptive. So if they span a very short width of distribution, they get shorter. So it may still look like they are sparse, but they are in fact very pointy. So the distances here are very, very small now. So they may be a little bit of a bimodal distributions, because perhaps different positions within their prior distribution may give similar results, like a circle. But all in all, they are pretty pointy. So there's pretty peaky distributions, except for this one. Perhaps within this range, the result will be the same, almost the same. But all in all, it just gets better. And sigma, which is the most important thing we see here, has gone from 2 to half. And the results are very much what we expected. Okay, any questions? So now I go back to the iPad, and let's see what happened, because you may have seen something strange going on there, in that this time it ran much faster. So it's time that I stop hiding this from you. You can run things in parallel, right? That's the main idea. And to do this, we expose something called conduits. A conduit would be like a tube or a tunnel to which we send the samples, and depending on what conduit we chose, they will fall on different bins or cans, so to speak. And each of these cans or conduits represent a different way to execute. Either, well, these are all we have. You can choose sequential, distributed, or concurrent conduits. And the default is sequential, as you may know, which is a slower one. It just runs one thing at a time. And this is good enough for, I would say, 90% of the thing you will do, because you may be using mathematical models that you want to, for which you want to infer parameters. And these are maybe very fast, and you don't need to think about parallelization. Why complicate yourself? However, for more complicated stuff, it can be MATLAB, algorithms, Fortran, LAMPS, any kind of prepackaged applications or legacy code or heavier stuff. You can use the concurrent conduit, which I will show you now. And for very big stuff, for large scale running in supercomputer stuff, we have created the distributed conduit, which will run MPI applications mostly. Disclaimer: the concurrent conduit can also be run in large scale, and we have used it for large scale execution. But it's a little bit more convoluted to do that, and we use it for the only reason that we run LAMPS, which is a what was it? Particular dynamics simulation, and it's very useful, but it's very hard to interface with. Such we say, okay, just run it and gather the results. But ideally, if you want to run in very large scales, you would use this one. Okay. So the sequential conduit is just as you imagine. There's only one process which will, one at a time and sequentially, run the samples that have been proposed by TMCMC or CMA. And when it's done executing all of those in the generation, it goes back. So it goes back to the algorithm and with all the results of the execution of the models. And I've shown you this already. This is how you run it. You define a model that takes a sample, easy. And then you say, okay, my objective function is the model. And then this you didn't have to put in your application because it's the default. But if you want it to be extremely explicit, okay, you can say I'm using the sequential algorithm conduit, and yeah, you just run it like any old Python application. So this is very intuitive, but of course it's slow, as we have seen before. So for the first steps to parallelize your korali applications so that they take 5 seconds instead of 40, you may want to start with the concurrent conduit. And with the concurrent conduit, korali creates multiple workers, all working in parallel. Each one will be assigned, or so to speak, a set of samples. And this is a technical detail. Korali uses a fork operation, so it creates multiple copies of itself, like a virus, funny enough. And each copy will know that they are a worker, and they will start executing the samples that the main process gives them. So there's a queue of samples to be done, and when the worker gets idle, it receives a new one. But suppose every sample takes the same time to run, then this is a very, they get the same 2 samples each. Then they send the results back and join the process, which means that they finish their execution and report back. And this is on only once the fork can join, but in each generation they get new samples to compute and they send the results back. And of course, in this case, things will be ideally 4 times faster because we have just, we are using 4 cores in your computer instead of just 1. And in the application, in the model, nothing needs to change. The model is just exactly the same, but you need to here specify explicitly, okay, I want to use the concurrent conduit, and I want to use 4 concurrent jobs at a time in this case. Now, the computer I'm using to show you the results and run stuff has 12 cores, and it also has hyper-threading. You may have heard of this. But hyper-threading is not good for the things we do. Hyper-threading, I don't want to go too technical, but basically allows cores to do 2 different things at the same time. But we don't want to do 2 different things at the same time. We want to do the same thing many times. So hyper-threading is not useful. This would have given us 25 virtual cores, 24, but we are not interested in this. So that's why when you see me running in the tutorials, anything in parallel, I will use 12 cores, 12 workers, so to speak. Okay. And then to run, it's the same. There's nothing to be changed. You just run this, and it will run like this, and it will work in parallel. It's as easy as that. So I guess the point is, we don't have a parallel TMCMC or a parallel CMA. We have TMC and CMA and all these other algorithms by default take advantage of the parallelism in korali. Korali takes care, so they propose samples and they don't have a say in how the samples execute. Korali takes care of execution of samples and returning the results. That means that if you want to develop a new algorithm for korali, you can easily do it. And okay, respecting some 1 or 2 rules that you need to abide by, you will get parallelism by default. So you don't have to parallelize your algorithm. Okay, so next practice 7. I guess this is a good time to make a pause, let this sink in, and then we can be back, let's say 2:05, and continue with the other examples. Okay, so see you then. All right, we're back. Let's go to practice 7 now. Well, I'm already there. And you can see here that in the folder practice 7, it's a copy of the solution of the exercise in practice 6. But now what you're being asked to do is to parallelize it using the concurrent model. So let's do that. But first, we need to know how to do it. So let's go to the documentation. Let's go to conduits. And let's choose the concurrent conduit. And it says, to use this, just write this line, conduit type concurrent. Let's follow orders. Let's go here. This is exactly the same code I showed you before. And it says, add conduit selection to parallelize your code. Okay, let's do that. I take it you can all hear me. So, okay, good. And we say conduit type concurrent. But this will not suffice because, okay, now we are choosing the concurrent conduit, but by default, and you can see it here in the documentation, the number of concurrent jobs it will use is 1, and therefore it will be just as slow as the sequential conduit. So what we need to do is to specify another value for this. And that value is concurrent jobs. And here we can say, okay, use 12, which is what I said I wanted to use in my computer. And it's, I guess we could have, okay, let's compile and run this. And you remember this is supposed to take around 30 to 40 seconds. We have seen it take that long. Now, just by parallelizing, it is taking us 7.5 seconds, so much faster. So here in the practice it says run with different levels of parallelism, which means use more and less and see what happens. So instead of using 12, we will use 6, and let's take note of how much it took. The results we know are fine. So when I say analyze, just take measurements and see what happens. And so with 12 cores, it took that amount of time. Now we recompile. Rerun. And say with 6 cores, how much time it took. I guess you all have an idea in mind of how much time it will take in this case, but perhaps you will be wrong because you would have expected it to take 15 seconds, but it took 12. In other words, using twice as many cores, we got less than twice as much performance. Does anyone have an idea why this happens?
There's time that needs to communicate between the cores.
That's one. Any other guesses?
Not every operation can be parallelized.
That's not true. So what happens is that we're using Monte Carlo processes, and in a broad description of Monte Carlo processes, it means that you can do many stuff, and all of this stuff is independent with each other. So you're running many samples, many computations that are completely independent from each other, and as such, it's the most parallelizable thing in the whole universe. And in fact, in terms of parallelization, there are very distinct categories of scientific algorithms or patterns of computation, and Monte Carlo processes are the most parallelizable. Meaning you should expect a perfect scaling. You should have expected twice as many. The answer is very computational. There's no statistical answer, there's no fundamental answer. It's very practical. And there are many reasons. One is the one you just cited. The other one has to do with internals of korali. So running the model takes very little time, all in all, or in the ballpark of what korali takes to communicate back and forth. So the noise that korali adds, the overheads, are factoring in. And the more cores you have working at the same time, the more noise there is while they're working. So there's one source. But this source of overhead dissipates when you run very large models. When the model takes an hour to run, then the fact that korali has added 1 second makes no difference. But we are still in the ballpark, so that's why a little bit of how you say, expected interference there can be. Another reason is pressure on memory. So we have 12 cores all running at the same time, and all are accessing a common resource, which is the system memory. And although they all have access to cache memories or they are particular to each core, they are competing, and they are destructively competing for this one resource. And the memory cannot feed all of them at the same time, all of the time. So that's why the performance gets reduced a little bit. And there's a third reason, but even this reason is not too bad, because when you scale up in many computers, then the memory resource gets also duplicated. So each system has its own memory. So the problem with memory gets bad to a certain point. The more cores you use per machine, but scaling in the number of machines you use will not affect this cost. So this cost has a limit. There's the most important cost is the cost that's prevalent at any stage of scaling. If you use a supercomputer, it will be the same as you use one computer, is loading balance. And we will see what that is later on in this lecture. But all of this to say, even though this is a Monte Carlo process, you should not expect a perfect scaling for architectural reasons, right? Okay, with this out of the way, there's another step, step 3. It says use the top command to observe the CPU usage, and this is just for you to see that this is working fine. Let's open another console. Let's see if we are bothering anyone. No one else is using the computer. And let's run again and see how much of the processor we are using. And you can see it here. This is me. There are 6 1, 2, 3, 4, 5, 7. Let me see. There are 7 processes. In fact, one is the engine, and there are 6 workers, but all of them are working on full use of their core. And with this, we got, it says 25% of the CPU is being used by us, which is a lie. It's actually 50%. But here, this command takes into account the virtual cores I talked about, the hyperthread. But this is just to confirm we're running in parallel. We're not going sequential anymore. Okay, so we are done with practice 7. Please do this at home later on. You will find it interesting, I guess. Let's go back to the iPad now. Good. We are here. Now let's talk about distributed execution. So the main limitation in principle of the concurrent conduit is that it's limited by asking the operating system create a new worker, and this creation of a new worker will always be in the confines of the same computer. So you cannot do this for when you're using 1,000 nodes, or well, the definition of a node is as an independent computer within a supercomputer. So if you use Pittsdane, which is the Switzerland's most powerful supercomputer to date, this machine has around 5,000 nodes, 5,000 computers working together or partitioned to work on different problems. So if you want to go more than one node, you need to start thinking in a distributed fashion. And this is what Korali provides in the distributed conduit. It allows you to run in more than one node. So for example, you may be running in nodes which each have 4 cores. And if we can use all of them together, we will have in total 16 cores available to do our sampling. And this is very easy to do. First of all, you need MPI to be installed. MPI is a communication library that gives Korali services for communication across different nodes. You don't even need to know what MPI is. The only thing you need to do is have it installed in your computer or in your supercomputer profile, and then use it and have it installed by the time you install Korali. Korali will detect it and grab it and use it. And there you go. You don't need to know anything else about the MPI. So in principle, you can say, okay, let's use the distributed conduit type, and nothing else needs to change. And you will be using the 4 nodes and all 16 cores. Each one of these working just like in the concurrent conduit, computing the samples that the engine gives them whenever they are ready. So the sample holds a queue with samples, and whenever a rank is ready, it will fit them, right? So to run this, it's not as simple as before, although it's still simple. You need to use what MPI has as a command to run your application. In this case, the most typical one is MPI run, but there may be exceptions depending on which system you use. Pittsdane has srun, which is an alias for MPI run, but it reports some, it creates some report and also loads some necessary libraries before it even runs MPI. And there were others, MPI exec, I think it's the standard. And there are other ones, well, I don't remember, but these are the 3 possibilities. Either of these 3 will work for you in the system you're using. And then the key point here is that you need to say how many ranks. A rank is what MPI calls a different process doing stuff. And there are copies of the original Korali rank, but Korali detects, thanks to MPI, that they are not longer, that this is not the engine, this is not the engine, any of these are the engine, so they take the role of workers. So it's like they multiply themselves 17 times, but only one of them take the role of the server and the other ones are working. That's why I say here 17 and not 16, because one of them should be the engine, okay? But then the calling your application is all the same, and the model is all the same. And never mind this. This is a typo. Okay. Good. So another way to work. Now you have used the distributed conduit. and you have learned about MPI, and you have learned how to parallelize the model itself with MPI, so the model can run in parallel by itself, without korali. And so if you want to use korali to run this model, you may want to, instead of running each rank running its own copy of the model, you may want to define teams. So these 4 ranks here, even though we are still using 16 workers, they will team up in teams of 4. And this will collaborate among themselves to run your model. And the model, and this is an MPI model, the model itself receives the sample, just like before, but also a communicator. In this case, communicator 0, 1, 2, or 3. And this is just a description of the subset of the ranks that are working here. With this information, when you do computation in your model, you can compute in parallel. So as you can see, there's 2 layers of parallelism here. The Monte Carlo process driven by korali with 4 teams, 4 workers, so to speak. And each sample is evaluated by a team of your model. The second layer, which is the model parallelism with MPI. So the way to do this is, besides describing that you want to use the distributed conduit, you should also say how many ranks per team or per sample. This may be a typo here. I think it's called team now. So how do you divide the worker space in teams such that they can all collaborate in the evaluation of a given model? Okay. And running it is all the same. There's no change in there. So any questions about this, either this slide or the one before? Okay. This is how it looks like when you're running it. This is an illustration of what I said. And the engine will start the experiment. The solver takes the execution at this point. It generates n samples. The samples are being sent through a tube, so to speak, to the conduit. And the conduit will distribute, in this case, the distributed conduit, 1 sample to each worker, as long as they are idle, waiting for stuff to be done. And this worker happens to have two cores, but it can be only 1 core. If you want to have twice as many workers than this, you can define only 1 core per team. But in this case, it happens to be this way because the user wanted to. So as soon as they receive the sample, they start working. And asynchronously, this may not happen at the same time and may not be always in the same order. One of the workers will finish and send back the results. But they are done, they're not idle. It is only after korali receives the results and tells the worker, okay, you're fine, that it becomes idle again. Then all of them eventually finish, all of them return the results. All of the results are sent back to the solver after post-processing. You know what this means, I already told you. And then we save the results, start again, and the workers are ready for the next set of samples to be executed. So at this point, the results are saved to a file, and it checks for termination. If it hasn't terminated, it goes again. So this is how it works. And this is the context of the supercomputer, and this is the engine. So practice 8. Let's go back to the code. So step 0, first of all, get a hold of an MPI library. If you go to OpenMPI, that's should work fine with korali, and that's an open source, free to compile and to use, and it even comes pre-compiled if you don't know how to compile it. So it should be pretty easy. And I would recommend it if you're developing computational models, or you're a physicist, or any discipline where you have models, that you learn this so that you can develop your own parallel simulations or whatever. So this is step 0. Now, step 1 says use the distributed conduit to parallelize the non-MPI based model in practice 7. So practice 7, I didn't actually show you the model. It's a Heat2D equation simulator, very basic. It employs a multi-grid to do things faster, to accelerate conversions, but there's no signs of MPI around. So this is, by all means, this is a sequential model, meaning only runs in one core. So we had already parallelized this using the concurrent conduit, but let's use now the distributed conduit instead. And this parameter is no longer relevant. And let's go to the documentation. The distributed conduit accepts 2 configurations. One is the number of workers per team, so how many workers we dedicate to each team. Since this is not an MPI model, we only want 1 worker per team because there's no collaboration. And there's no second layer of parallelism. And then communicator is the subset, so this gets a little more complicated. The subset of the available MPI ranks we have, how many do we want to dedicate it to korali? But if you don't specify anything, we would use all of the MPI ranks we have at hand. And the workers per team by default would be 1. So this is all we need to do to parallelize this code. When using MPI, since you may not know this, you need to be a little bit careful with the outputs because all of the ranks will do the same. So instead of waiting for it to fail or have some weird behavior, I will just remove all of this. And you know already this is working. So let me at least keep the results. Yes, the results are going to be stored. So let's run this, recompile. And say, okay, MPI run, don't forget about that. And since we have 12 cores, I'm going to use 13 MPI ranks. And then run this. And also I want to take a look at what's going on here. I failed to do something. When you use MPI, you need to initialize MPI. And I forgot to do that. And this is just a detail. And something I didn't mention before, there's a lot of examples of all of the things I'm saying already in the korali code. There's a tutorials folder. You have everything I'm saying here. There's plenty of examples of how to do it. So don't be scared if you don't know what MPI init is. Just the call to initialization of MPI, nothing more. So we compile again. And we run, and you can see here, it's effectively running in parallel. But now the difference is that if I had access to a supercomputer, this is just one computer I have at hand now, but if I have access to 10 computers, I could say, give me 12 times 10 plus 1, 121 ranks. And you can see here how easily it would be to scale this up to 10 computers or 120 cores, just as easy as that. Okay, so now it says here, step 2, go to folder practice 8. Let's take a look at what there is there. Let's clean. Now it says, have korali run the MPI-based model there. So let's take a look at the model first. The model is a Jacobi solver, pretty much similar to the one we used in the previous example. But this one, you can see here, has some MPI calls. And there's at some point, MPI communication. And you don't need to know about this, but this is data being sent and data being received. So that's boundary data that neighboring ranks need to receive to collaborate and work together. So this is a perfectly fine MPI-based solver that can run in parallel and multiple cores and nodes by itself without korali. So what it says here, fix the number of ranks. So it says always use the same number of ranks. First it says have korali run this. So here we have the init already there, the initialization of MPI. And as parameter, this program receives the number of workers per team we want to use. So it's automatized, nothing else to do, except to configure korali to use the distributed conduit here. So we can say conduit type distributed, and then conduit workers per team, and all caps. And we have the value here, it's this one. Okay. It also asks us to configure the profiling information. We'll see what that is. Let's just continue now. We'll see it later. So let's just compile this. And now let's use our 13 MPI ranks to run this as it has been compiled. And the name of it was practice 8. And now it says, okay, fix the number of ranks to 13. And let's analyze the execution times by changing the proportion between the number of teams and the number of ranks per team. So in this case, I'm going to run 12 workers, each one running a team of 1 rank. So there will be 12 concurrent model executions. Something went wrong. What is it? Segfault. I guess I should grab the. Of course, this can always happen with when working with C++. It's strange. Let's take the solution. This one should go fine. I don't know why that failed before, but okay, whatever. I forgot to specify. Okay, so we're running 12 teams of 1 rank each. And we want to measure how much time it takes to reach 50 generations, I think. Yes. It took 9 seconds. So it's 12 teams, 1 rank each, 12 seconds. And now let's do something different. Let's do 2 workers per team. And this will mean that we run 6 teams, 2 ranks each. And this will take how long? A little bit less. Now let's go even further. 3 teams of 4 ranks each, I guess. It took even less. So there are reasons by which you would like to play around with the 2 levels of parallelism, the Monte Carlo one at korali, and the internal parallelism of the model. And typically, you would like to favor assigning the most rank, or the larger amount of teams for the Monte Carlo process, because it's completely parallelizable and it's almost guaranteed to have perfect efficiency. The level of parallelism inside the model, since it's communicating stuff around between the workers in the team, it's supposed to be slower, in the sense that it's supposed to be less efficient when you assign more parallelism to that layer, to the model, than the Monte Carlo process. But what's happening here in particular, and against that intuition I just gave you, that heuristic, the reason why this is going faster, the more, the bigger the teams are against our practical reasoning, is that we have a very large model being run in the system. This is only one node, only one computer, and the model is very memory intensive, meaning that the fact that we're running 13 grids at a time, 13 problems at a time, means that we are using a lot of memory in the system. But when we chop it finer and we say, okay, only run 3 at a time and keep the computational power to each of the teams, we are reducing the impact in systems memory, and that's why it's going faster. We are running much less smaller grids, not the same size of the grid, but less grids. This means less presence, less footprint in memory, and this means that the data can be better cached in the L2, L3, L1 caches of the cores. This is the only reasoning. But other than that, when you scale up and up and up and up, you should always give more parallelism to the Monte Carlo process, because it's guaranteed, and there's no communication, it's guaranteed to be more efficient. I hope I drove the point across that there's a heuristic, but it may fail at small scales. So I guess even the better tip would be to say, always try different configurations. So be empirical. Don't try to theorize when you're talking about parallelism, because there's things that are beyond your knowledge, architectural stuff that even you would not know about, and so try different ways before deciding on one. Okay. So it says, configure korali to store profiling information and use the profiler tool to see the evolution of the samples. So what is this? I would ask you to go to using korali, go to parallel and distributed execution, go down below, and see here that you can obtain profiling information by adding this to your code. And here's this, I took it from the solution. It's already there. It says enable profiling. I guess this changed. I will update the syntax for this. So this should be the one to use. You should say the detail of profiling should be full, complete, and then the frequency in which you want data to be saved into a file. And here, since I already run it, this is the file that has been produced by Korali, and we can read it by using the profiler tool. If you go to tools, sorry to be moving around so much. There's a tool called the profiler, and it has some configuration, or in principle, you only need to say, okay, give me this, show me the profiling information from this input file. It may take a moment to appear on the screen. In the meantime, if you have any questions. Okay. So this is a bar in some small bug in the representation here. This is how it looks when you run Korali. The blue blocks means times where the worker team was busy doing stuff, processing a sample, and the white blocks or segments means that the cores were idling. And the reason why they could be idling is, among others, but the main one is load imbalance, meaning that, let me show you, go back here. If you take a look at the code, we're using 12 CMA samples per generation. And suppose we have 12 teams working together. All of them should finish before the next generation starts. If one of them takes longer, all of them will have to wait for it. So the white segments you have seen is just workers waiting for the others to finish. And this is the biggest source of inefficiency when you're running on large scales. There may be one outlier, and this may be given by the fact that the computer had some problem, or it can be due to the fact that the parameters of the model make the model take longer. It may be, the parameter may be the speed of a car, and thus the car will take more simulation time and also thus computation time to finish, to reach the end line. And therefore, that single sample will make everyone else to wait until it's finished. I will illustrate this better later. I guess the main takeaway of this practice is that you can use the profiler to have a visual representation of how things worked. And we will use it again, don't worry. Okay, so let's go back to the iPad. And I guess there was a question about this. How do we run applications that are not interfaceable? So you cannot include it as a Python module, or you cannot link to it with MPI, with C++. And these are typically called black box or out-of-the-box applications. So the application is a black box. You don't have any way to understand how to link with it, how to interact with it directly. The only thing that you as a user have is that you can execute it, give it some parameters by console or by file, and it will print out in the console or in a file the results. You don't know what's happening inside or how to, it's pre-compiled even. There's no way, there's no code around. So you can still use these applications with Korali. And this is what you do. We will create a model. This we do, we create a model like everyone we had before. We grab the parameters, X and Y, for example, and then we ask the operating system to run this application. This is completely fine with Korali. You can just run an application like that. And you say, this is the path to my application pre-compiled, and these are the parameters. Say this is the way the application runs when you run it normally. You give it parameters X and Y by console. But it can be a file. It can be an input file, right? That you provide, that it will read from, right? Either way, so you can be, instead of running, you can, before running, you can be saving these parameters to a file and then run the application without the parameters. So anything can go. Then the application will save the results to a file or to the screen. Either way, you have ways to grab that, either by parsing the result file or by taking the results directly from screen. Not that one, this line here. You parse the results from the file after the application has finished, and then you save the results like that. And then you go. You create a model that calls an application, which is a black box. And the only conduit that is capable of doing this is the concurrent one. There's technical reasons for this, but if you try to do this in the sequential conduit, you will override Korali. So when you run this application, it will replace Korali, basically. So you will run the application, but then forget that you were running Korali. So that's no good. If you use the distributed conduit, it will use MPI, and MPI is not a fan of doing these kind of things, unfortunately. So the only way to do this is to use the concurrent conduit that uses the fork join operation that is very compatible with doing these trickeries. And you can have it working in parallel. So you can have 12, 24 workers at the same time executing this closed box application and gathering the results, right? This doesn't mean that you cannot do this in a supercomputer. And in fact, we use this approach to run lamps in a supercomputer in 4,000 nodes. So you will be wondering, how do you do it? Because if you're limited to using the concurrent conduit, you cannot go further away from the single node you have. Well, you can. If you run, instead of this command, you run something like MPI run, and believe me, this can be done, -n24, and you define 1,000 concurrent jobs, each one running one of these, you will be running, if you're careful, 1,000 nodes and or samples, let's say, but in reality, and this will be 24K cores. So you can play around, use the concurrent conduit to run MPI as a second layer, but once you get, you will not get to this point. And if you get to this point, you can send us an email and ask us why, but also there's also an example that in the Korali code that does this. But this is a very advanced, and if should you need it, we are there to help you do it, okay? And then you run it the normal way, so there's no MPI here, it's just you run it normally, okay? Oops, so the iPad is kind of low to erase stuff, so we have time for questions. Any questions so far? Okay, so practice 9. Practice 9. Says, let's examine the model. This is our black box application. Let's suppose that they don't have access to this. And this is an application that takes n parameters, and with those n parameters, it does some calculations. We don't really care about what these calculations are. They are artificially complex, but the point is that we have the application, and we can run. Any number of parameters we can give it, and depending on the values and the parameters, or yes, the number of parameters and their values, it will output a different number, and it has a reason to be. So there's a function underneath this that can be inferred. But in principle, we assume that we cannot look at the code, nor can we import the code, basically. So this should not be here. And then we should create our own model, which is tasked with running that application as an outside application. And since we don't have too much time, let me jump straight to the solution, but you should try to do it yourself with the instructions there. And the idea is that this should also be taken away because we don't have access to that. You will have the path to the model, and then you will have the list of parameters to give it as defined here in the problem. So we have 4 arguments. So you will receive 4 arguments. And the arg string is the command line string that you want to execute. And besides the path to the executable, you will add each of the parameters as text. This is a number, but you convert it to text and you append it to the command line command. And then you can run it with this Python operation. There are several of them that can do the same thing, but this is the one I chose to use with the command line and the arguments we had calculated. And then we can decode, that's the operation we do with the results. Decode the output to screen. So you saw that the model prints to screen, it doesn't save a file, but it could be saving a file. No one says, there's no restrictions. And we convert it to a number, which we save as f of x. So you can see that I can just run this. Okay, this is this way. running the Python code we saw with the weird function without ever importing it. So there's no importing it. I'm just running it as command line commands. And it will be interesting to see what this command tells us that's happening while we run that. Okay, it's all Python, so that's not interesting. Never mind. If it was a C or precompiled application, it would show you here the name of the application that is being run by your model. And I guess the only interesting thing to do is to run this in parallel. You can run a black box model or application in parallel also. There, much faster. Okay, so let's go back to the iPad, and I will leave the practices for you to do. There's the solutions there, and I will jump straight to the theory. I guess rather than theory, the things you can do. And this is something you can do as well. You can run simultaneously multiple experiments, and they may or may not be the same nature as the same experiment. One can be optimization, and the other can be sampling. Typically, they will be the same experiment, but with different input data. If you want to do hierarchical Bayesian analysis, you will run n Bayesian inference experiments, but with different input data, reference data, and then you compare the results to gather some hyperparameters or whatnot. So Korali starts both experiments at the same time. They will feed the conduit with samples coming from the two experiments, and they will be given back and forth with the workers in any order, so long as to keep the workers busy at all times, right? So the worker doesn't care which experiment it comes from, it just executes whatever is given. That's the main idea, right? There's nothing else to say. What's the effect? So you have seen, I show you that the main problem when running at scales is that TMC for MC in this case, for example, there will be, for each generation, these are 5 different experiments run one after the other. So each color is a different experiment. There will be samples that take longer and samples that takes less in the same generation because of the variances in running time that the parameters give to the model. And this causes some workers to remain idle, and we calculate this idleness with a number called efficiency, the cumulative efficiency. So at this point, how efficient it was, how occupied with color was this timeline, as opposed to idle with white segments. And you can see that if we run all of these experiments sequentially, we get around 70% efficiency. But if you use Korali to run them all together, what you will get is that the workers, when they are waiting for the samples in the current generation of some experiment to finish, they can grab a sample from another experiment that is waiting to execute. And so you get this colorful pattern in which the worker speculates and grabs whatever work is available as soon as it finishes, and thus we can get a much higher efficiency, in this case almost 98%. So the motivation to run multiple experiments simultaneously is not in terms of it's not for practice reasons, it's not practical, although it may be that you just define it once with the for loop and then you just run all of them, but instead it has to do with efficiency at large scales. And I prepared a practice 10 that you should run at home. Well, you're at home, of course, but you should run yourselves, in which you will see that even in this specific case, is tailored for you to see that you can improve the efficiency even when you're using a single node, because the phenomenon of load imbalance happens even in single node executions. So take a look at that, try to replicate and come back to me if you have any problems. Then lastly, this is something also very interesting and doesn't have to do with how many computers you use or the scale of where to use, but rather how long will it take for you to run the experiment. So you may define an experiment that takes too long. And God forbid something happens to your computer while you're running this, or the light goes off, whatever reason, after 3 days of computing, just before it finishes, it goes off. So you lost 3 days of results. So Korali will prevent this from happening by saving the entire state of the experiment at each generation for all experiments. So suppose you're running in 4,000 nodes, wasting a lot of money, not wasting, but just spending a lot of money in compute hours. And we are talking about hours here, or even days. At each generation, Korali would save this whole state of execution. There's nothing spared. Everything that can be saved, it will be saved. And suppose at some point a fatal failure happens. It's out of your control in the middle of generation 4. So what you can do is relaunch the experiment, or rather the application that contains multiple experiments or just one. Korali will take, well, under your instructions, it will take whatever it was before as starting point, such that you only lost this amount of time in computing power that you were computing generation 4. When you restart, you start from the same point you have set here, and then you get the results for generation 4. And then you can continue going. So whenever, if you are faced with the possibility of running an experiment for long times, be assured that even if you didn't think about it, if something ever happens that breaks the execution, you can continue from the latest generation that has been already saved to the hard disk. Unless you disable file outputs, which you can, but I don't recommend, right? If you do it, I'm sorry, there's nothing I can do. Okay? And then the final one is saved, and then you got the results. And this can be done for any possible solver problem and content combination. It doesn't matter what you use, what you do, this will be true always. And not only that, the state of the random number generators are also saved, such that you will not only get continue your execution, but you will get the exact same results you would have gotten if nothing happened. The exact same results. So there is some reproducibility aspect to it that is very valuable. Okay. So practice 11 would be for you to go to the code and follow these steps and realize that what you can do with Korali in this sense. I think this is a very good moment to stop the explanation, and we have a few minutes. If you have any questions, shoot out, and I'll do my best to answer. I may be wrong, but I think George will use Korali for his explanation if he didn't use it already, Gaussian processes. So I try to explain the technical aspects and the things you can do more than an extensive set of examples as to the specific modules Korali has, reinforcement learning or other type of inferences, or that I left that to George. But if you have any questions, this is your moment. Otherwise, you can shoot me an email. I'll do my best to answer as soon as possible. And in the future, when you're working on your own stuff, and you may think Korali is a good tool to use at this point, and you have questions, also shoot an email, no problem. Otherwise, if no one has questions, I assume it went really well. And I thank you for participating, for being here, and I hope to have you as users of Korali in the future. Yes? I have someone? Okay, Then what I do is stop recording now.